So here we go. So we're going to talk about how we solve one-way slab a little bit more today, just a short example basically. And then we'll extend our deadline to this Wednesday before the exam as a new deadline for the homework. I will send an email reminder also after the lecture, okay? So that's that. And the other thing for the exam, we're gonna have a review session tomorrow in office hour, 2 o'clock. The review is now directly related to the specific problem in the exam, but it's just a general review of what we talked about so far, the shear and one-way slab. So please do attend if you have time, and I will send link beforehand. Okay, so that's that. And now we're going to talk about the serviceability deflection. But before that, let me share my screen. So let's take a look at what about this one-way slab, right? Something about our one-way slab. So let me just turn it on. Okay. So this is some of the figure I drew the other day to help several students who have question about it. Okay. And we're going to iterate a little bit about how we're going to solve a one-way slab. Yes, the review will be recorded since I will not be showing the specific problem for the exam, but in general of some of the quick tips for the problem, okay? And then this, again, coming back to this figure here, this is the one-way slab drawing in plan view and trying to illustrate what kind of structure we have, all right? This is the homework. This is the homework. So I'm gonna redraw it real quick to give us a better idea what we're dealing with here, okay? So now, first of all, I have, these are columns, right? In the homework, these are columns. You probably see the similar things in the exam as well, okay? These are columns. This small tiny blocks I'm drawing here, these are the columns, okay? I repeat, these are columns, okay? And now I have, say in this case, I have more than two spans, right? So I need to have four columns in each direction, okay? And then once I have that, I have to have frame. So my frame goes this way, right? So I'm just gonna use a thicker color, black. So this is my beam. This is my beam, okay? This is my beam. And this is my beam as well. So former grade, right? Former grade, all right? And now if I call it one as, call it A, B, C, D, these are my base. These are my base. And then I call it grade 1, grade 2, grade 3, grade 4. Okay, these are the transverse direction, right? These are the transverse direction. Now on top of this, I also have small beams across these grade, right? So I call it 1 prime. Okay, I have the other one, 2 prime, 3 prime, going on like this. Okay, now we have different span lengths, right? Right? So let's take a look. So I say, right, let's call this 24 feet, all right? Some reason, right? I just want to call it 24 feet, okay? So this is, say, 32 feet. And this is 24 again. Okay, and then I say, okay, now between this outside beam and the interior beam, I have about 10 feet. 10 feet, etc., etc. All uniform, right? All uniform. 10 feet. All right. So before I start solving my problem, the first question is where or which direction is the one-way slab direction? Okay. Which direction is the one-way slab direction? So how do I tell? How can I tell, right? So I'm gonna say this is L1 direction. Oh, let me call it L2 to be consistent with the lecture notes, okay? This is L2 direction, and let's call it, this is L1 direction, okay? All right, this is L1 direction, okay? Now, the one-way slab definition is that if I assume L1 is the one-way slab direction, right? So L2 over L1 has to be bigger or equal than 2. Bigger than equal than 2, right? So this, in this context, right, the L2 equal to what? 24 feet. This is the minimum span length. And L1 equal to 10 feet, and this is the maximum. Well, it's the same across the board, but I'm just gonna say this is maximum, right? And now I would say that L2 over L1 is almost 2.4, which is bigger than 2. So I have a one-way slab action, along L1, right? So I'm just gonna use my different colors here. So now with one-way slab action, right? One-way slab action is right here in this direction. I'm gonna draw the strip, right? This is one-way slab. This is one-way slab, and this is 12 inches, 1 foot as the strip width, okay? All right, so this is the one-way slab. This is the one-way slab. All right, now if I want to solve for this one-way slab, if I want to solve a one-way slab, what I'm gonna do, I'm gonna use a different color here. I'm gonna do a cut here, okay? So I'm gonna do a cut right in the middle of it, and then I'm gonna do this. The arrow here shows that we're which direction I'm looking at the cross section here, which direction I'm looking at the cross section here. So after I do the cut, right? After I do a cut, okay? After I do a cut, what I actually see is this way. I actually see what? I actually see this. So I'm gonna use blue, okay? So I'm gonna use blue here. So correspondingly, I have, this is basically the column underneath it, okay? Since it's cut in place, everything's together, so I have a beam, right? I'm talking about this right here, okay? I'm talking about this right here, all right? I'm talking about this right here. So underneath it, do I have a column here? No, I don't. Okay, this is one-way slab, so I don't have a column here. You can see that, right? I don't have a column here. So actually what I have is a beam. I have a beam. I have a beam, right? So I don't know the beam dimension in this case yet. I don't have the beam dimension. So based on the homework, I'm gonna say all my beams, right? All my beams have 18-inch multiplied by 28-inch of dimension, right? 18 by 28. What does it mean, right? It means that for the beam, I have a dimension of 18, which in the width direction right here, and I have a height of 28. Okay, so this is my beam direction, right? This is my beam direction. Okay, now here I have actually this showing here is the beam. Okay, and this is actually 1, right? Grade 1. So 28 is right here, 28 inches, and 18 is right here, 18 inches. Okay, 18 inches. And I would say that also the slab has a thickness of 6 inches, right? So HF or H equal to 6 inches. I really don't like this pencil too much. HF equal to 6 inches. Okay, so now with that, I do know in my case, I have a slab on top of it, and this is my slab, and my slab has 6 inches right here. Okay, and that's my slab. So I have my beam 1 here, okay, and then I go along, right, and talking about this joint here, right? So I have 1 prime, another beam right here. So this is my 28, this is my 18. Continue on like this. Okay, and then I meet here. Where's my 2? It's right here, and this is 28. This is 18. Okay, so this drawing go on and on and on and on, right? Until you meet the end of it, right? Where you have ... 4, and this is 18. This is 28. Okay, so that's the structure, right? That's the structure. And then the question is asking, what is a moment coefficient? What is a moment coefficient? So you can take this drawing and compare with that table we provided you from the lecture notes. and find out the coefficient. Find out the coefficient. Now, the trick question is, not trick, but the important question here is what's the span length? What's the span length? So this is the span length. This is the span length, but be careful, this is Lm, clear span length. So Lm equal to L, which is the span length, minus half of the beam width, BW, minus another half of beam W, left is right, left or right, right? Since they all share the same width, so we have 10 feet minus half of, in this case, 18 inches. So 18 inches converted by feet divided by 12, and minus another 18 divided by 12, right? Right, so now I have this equal to 10 feet minus half, bracket inside, this is 36 divided by 12, right? So this is 3. This is 10 minus 1.5, so I got what? I got 8.5 feet. So that is the clear span length. Some of you are asking, okay, why do I need a clear span length again, right? So here, when you calculate the moment, right? For example, if I want to design a one-way slab, I'm looking at a moment here, the maximum moment here, positive. And I'm going to look at a negative moment here, negative, right? So for example, if I say the moment coefficient here is 1/24 minus, right? And the middle is 1/16 positive, right? And these just example, you can look up the table we provided you from last lecture and find the exact number. But say if the negative moment is minus 1/24, this is omega u L n squared. Omega u L n squared. This is where you use the 8.5 feet. This is where you use 8.5 feet. Okay, that's the clear span. All right, so that's first. So have to identify the structure. Okay, have to identify the structure. All right, now this is first. Now the other thing is, what about omega u? We don't like this pencil too much. Omega u, what is the distributed load, factor load? Okay, what is the factor load? So when I look at this, right, I have to take a look at my strip right here, So since it's red, I'm gonna go back to the color red here. Okay, I'm gonna go back to my color red here. So this is my 1 foot slab. And to be specific, this is the strip, right? This is the 1 foot strip I was talking about. So this is 12 inches, okay, 12 inches. All right, and don't forget, it's per foot. It is per foot. Whatever loading you have, it is per foot. Okay, so now what is this per foot business, right? So I have basically, this is a distributed load on top of it. Distributed load on top of it, right? And let's call this live load omega LL, omega L. Let me just say, I tell you if omega LL is 150 pounds per square feet, okay, 150 pounds per square feet, okay? Now, what will be the distributed load? What will be the distributed load on this, right? So first of all, I have to say, now, let me not use omega LL, okay, to be differentiated. I just say this is live load, okay, live load, okay? And I say dead load is the self-weight, okay, self-weight. I need to compute, okay, I actually need to compute what is this omega u equal to 1.2 omega dead plus 1.6 omega live. So I need to compute dead and live. All right, so the easy thing to do is, what is the live first? This is not right, this is omega L. What is live load first? What is it, right? So the live load actually equal to the live, the 150 pound per square feet, multiplied by what? Multiplied by what? Multiplied by the area, right? Multiplied by the area, right? So I have per foot, this strip direction. I have another per foot, linear foot in this direction, don't forget, because this is long, the span length, right? This is long span length. So I have live multiplied by 2 units, right? I have live multiplied 12 inches. This is 1 unit, so 1 foot, essentially. Okay, and I have another one, which is, so this is basically here. Let me just show you what I mean by that. And this is another foot by the strip. Okay, so I have distributed load, I have area, I need to get a pound, right? Basically I get a pound. So this is 100 pound lbf per feet squared multiplied by 1 feet multiplied by 1 feet. Okay, so eventually I got is omega LL 150 pound. That's it, because the feet squared canceled with feet squared, right? Feet squared canceled feet squared. Okay, so this, what does it mean? It means, all right, it means this is pretty straightforward. It means this 1 foot by 1 foot area, 1 foot by 1 foot area, right? I have 150 pound distribute load on it, distribute load on it. All right. Now, coming back, think of it, right? Think of it. What we're talking about in terms of omega LL, right? That is actually per linear foot, because we're thinking about in this direction as a unit distributed load, right? Unit distributed load. So have to divide it by its unit. So it's per linear foot, okay? And also we have to consider that goes on this direction, right? Because it's a strip. So this is also per linear foot. And now I divided it by twice, so I have per foot squared, per foot squared, okay? So now I have per foot squared, okay? So don't forget. So you see the unit come back, the unit comes back, the unit comes back, okay? So that is actually 150 pound per foot in one direction and per foot in another direction. So you have a foot squared, I have a foot square, and this unit is the same as in the lecture notes. That's where I get the unit. Okay, that's where I get the unit. Okay, all right. So okay, so this is how we calculate the distributed load. What about that? What about dead load? Right? What about dead load? Okay, this is a little bit tricky now. So for the dead load, so for the dead load, let me zoom in a little bit more so you can see better. So this is the volume. This whole thing has the volume of the concrete, right? This whole thing has a volume of concrete. So let's take a look at the dimension of this unit, right? This unit. So I have a foot going this way, going this direction. I have another foot going into this direction. And I have a height of 6 inches, okay, going this direction. So the unit volume, okay, per this unit volume of this slab here is 1 foot by 1 foot by 6 inches divided by 12 foot, half foot basically, right? So the unit volume here is basically, this is 1, this is half, so 0.5 feet cube. That's my unit volume. That's my unit volume. Okay, that's my unit volume. All right, so I want to compute how much total weight. So total weight per unit, total weight, self-weight, okay? Total self-weight per unit volume, right? Per unit volume. Equal to what? 150 pounds per feet cube. That's the density of the concrete, right? That's the density of the concrete. Multiplied by 0.5 cube, right? Foot cube. So I have basically 75 pounds per this volume. So that's how much of force, how much of a weight I have per this volume, okay? But here, this is unit volume, right? I also want to convert it to a dead load, So that would be the 75 pound, okay, per foot in this direction again, and per foot in the other direction again. So I'll have per foot squared, okay? All right, so that's the dead load. That's the dead load. Okay, now if I want to compute a total factor load, omega U now is 1.2 dead plus 1.6 live. Okay, so that is 1.2 dead. What is the dead? Dead here is 75 and plus a 1.6, 150. Okay, and the total unit is 0 pounds per feet squared. Pound per feet squared. Okay, and then I get what? Let's do a simple calculation. This is 1.2, right? So I got 75 plus 15, right? 75, so 100, right? Did I get it right? Okay, I need to punch my calculator. My brain is not working today, okay. Calculator, where's my calculator? 1.2 multiplied by 75. Oh, 90, yes, close. That was what I was thinking. So 90 plus 1.6, this 240, and this is pound per square feet. So I got 330 pounds lbf per square feet. Okay. All right. So this is the final factor load for the slab. All right. Now here I have factor load. What about moment? Right. So eventually we're going to talk about a positive moment or negative moment. So let's, for example, the positive moment equal to 1/16 omega u ln squared. So this is 1/16 omega u is 330 pounds per foot squared and multiplied by 8.5 feet calculated before squared. Okay, 8.5 feet squared. Okay, so what I got is, this is positive moment, is 1/16, right? This is 1/16. I have 330 pounds per unit. So 8.5, what is 8.5 squared? Let me just write it out, 8.5 squared. Okay, what I'm more interested in is the unit. Okay, let me show you the unit. So this is pound. This is pound per feet squared. Okay, and I have a feet squared. Okay, I have a feet squared. Okay, now let's get this number out. You can take a look at yourself. This is 1/16. So I'm just gonna punch all the number out. So just for convenience, it's 330 multiplied by 8.5, multiplied by 8.5. Okay, so that's that, and divided by 16. I have roughly a 1,490. Okay, that's the number here. Okay, and this unit right here is strange. Why? Because it's pound. Because it's pound. Okay, so if you left like this, I would say yes, your calculation's right, but does it make sense to you? That's the question here, right? Does it make sense to you? Okay, the answer to that question is no, it does not make sense. Why is that? Because recall, moment, right, equal to force multiplied by distance. In a common unit here, we're talking about pound, lbf, multiplied by feet, or better yet, kips multiplied by feet. That is 1,000 pounds, right? 1,000 pounds. So what I'm looking for is moment in terms of 1,000. So this is actually 1.49 kips. Where is my foot in this picture, right? Where's my foot in this picture? So this is what happens. Actually, I need to multiply by a foot and get my unit for the moment and divide by a foot. Divided by a foot. So why you do that? Because now, if this is the case, I'm going back to my strip, and this is moment, actually positive. Okay, per foot, because this is 1 foot unit length. Got it? So that's why you have this in terms of pounds or kips. But matter of fact, you need to write it this way: kips foot per foot. Okay, and this is very important in the exam because I will be looking for this unit in the exam, right? In the exam, kip foot per foot. Okay, so for those of you who has paid attention from previous lecture, you find out this is unit we have. Okay, but we didn't elaborate on how we got here. So today we have elaborated on how we got here. Okay, all the details here, right? All the details here. Okay, now this is only for the slab. This is only for the one-way slab, right? So I want to make a notification here. Note here, this is one-way slab. All right, this is not a beam yet. So the question is, what happened to the beam, all right? So if I take a look at the beam here, okay, it's in a different direction. Okay? And again, if I do a cut on the beam, right? You'll see a different view. You will see a different view. Okay? For instance, if I do a cut on grade 3, right? What I see. So on the beam, grade 3, along grade 3, what I see is I see the column, because that's actually there, and I see the beam, which is across this way, okay? And I also actually here, be careful. See, when I cut it here, right, cut it here, I see this beam on the side. I also see this beam on this way, right? So matter of fact, this drawing is not complete. This drawing is incomplete, okay? So it's incomplete. The real drawing, this is the column. And from the homework, right, I say this is 18-inch by 18-inch of a column, okay? And I have a beam, which is running inside, outside plane direction, and this is 18 inches as well. On top of it, I have my slab, I have my another beam, and this is another beam, 18 inches, okay? So that is the beam along 3. That is the beam along 3. So you have the column, you have the edge beam, and you have the beam of the question, right? Beam of interest. You have the beam of the interest. Beam of interest. Okay, so this is what? This is when I cut here, when I go back to this picture here, when I cut here, right? I see this drawing here. Okay, so when I move along this way, I see another beam here. So this is A, bay A. Okay, I see the same thing here, somewhere here at, so this is actually joined together, okay? My horrible drawing, sorry about that. And let's just connect them like this. And this is B, okay? Go on, this is C. And near future, right? This is all the way down here, D, okay? D, is that right? Let's check, right? So I have beam running this direction, 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 beam running this direction. So I have 2 directions, right? So I have all of them, right? I have all of them. So this is the beam 3, grade 3 that you're looking at. And now span length here, this is what? This is 24 feet, and this is 32 feet, and this is 24 feet. So if I were to ask you to find out the moment coefficient for this case, right? Be careful, you have an uneven beam span length, right? So make sure this 20% rule. So 32 divided by 24 is what? This is 8, this is 6. So, so this is essentially 8 and 6. This is 3 and this is 4. So it's 1.3, slightly bigger than 1.2. So the ACI table does not apply. Okay, does not apply. So this problem you cannot solve by ACI table if I have 24 feet, right? If I have 24 feet. But in the homework, I believe, I changed this number to 28. Right? In the homework, I have 28, okay? Let's just say it's still 28, right? It's still 28, so let's remove this to be a 28, okay? 32 divided by 28, so I have 7, 8, so I have a 1.14, right? So it's smaller than 1.2, so ACI applies. ACI moment coefficients applies. Okay, then if it's 28, 32, I have 2 span, adjacent span within 20% of difference, then ACI applies. Then I can go back and use that table to find moment coefficients. Find the moment coefficients. Okay, all right. So why I first use 24 feet, that's a hint, right? Because in exam, you might see a different span length there. So first thing first, you need to show me that it actually satisfies the requirement to use the moment coefficient table from ACI. Okay, to use the moment coefficient from ACI. Okay, all right. Then the subsequent calculations are similar. The subsequent calculation is similar to the slab. Now the difference is now you know, if I draw the cross section, you know the beam. You know the beam. So this is actually 18 inches, right? 18 inches. This is 28 inches. So when you calculate the omega L live load, this is live, and omega dead load, you use the similar approach as we did before for beam design. Use the similar approach did before for beam design. See beam design, okay? Don't do the same as slab, right? The slab shown before does not apply here, okay? This is beam, right? This is beam. So that's the difference if you calculate for beam, okay? All right, so I know this is a lot to take in, and the main reason I think behind it is actually you need to study a little bit more from what we taught last lecture, okay? So all these information that I talked about here today were contained in last lecture, but we didn't break them down into such as fine details. All right, all these details are collapsed within the previous lecture. So when you go over the previous lectures, right, you can correlate the details we offer today to the content we have from previous lecture and seek logic behind them. Okay. All right. So that's what I'm gonna say about the homework and specifically about one-way slab action and all this moment coefficient business. Okay. So that's probably it to end the serviceability in terms, sorry, not service, to end about one-way slab. All right, to end about one-way slab. Any other questions about it? Before we move on, any other question about it? Okay, if it's quiet and silent and forever hold your.
Oh, I got a question.
Go ahead.
Okay, so for the beam design then, when you find the dead loads and live loads, does that mean you're going to find them in linear foot?
Well, think of it, right? Well, what we did for the beam design, right? Previously, when we did beam design, right, we used the same cross-section area multiplied by the density of the concrete to get the dead load.
Right.
And then we have a live load and multiply by this width right here, right? Remember, to get load pounds per linear foot. So for the slab, you get a pound per square foot. Per foot, right? For beam, you only get per foot.
Okay.
Right? So there's a foot difference there.
All right.
So if you forgot about it, if we forgot about how we do beam, you can always go back to see the previous lecture notes.
Right. Okay.
Yeah. So be careful, okay? Yes, indeed. In the exam, I'll be looking for the unit there. For the slab, it's always for the distributed load. After you calculate everything said and done in the factor form, it should be pound per foot squared. For beam, it's going to be pound per foot.
Okay.
And in terms of moment for the beam, it's just pounds foot or kip foot, right? And for slab, one-way slab is going to be kip foot per foot.
All right.
Right. So that's the difference there.
And then I've got one more question about the moment coefficients.
Yes.
So in the handout that you gave us in one of the previous lectures.
Yes.
For the inside supports, yeah, yes. That one. So for the inside supports on the left and right, you had different coefficients. So
here?
Yes.
Okay. Yes.
Right.
Yes.
So we are using both, right? Since we're getting a moment on either side.
That's right. That's right. You use both. You use both.
Okay. All right. Thank you.
Well, yeah. Just to clarify, now you have 1/10s, right? You have 1/11s, right? 1/10s is on the left side of it, and 1/11s on the right-hand side of it.
Yep.
Okay. Just be careful, right? Why is that? You got to think of it, right? Why is that? Look at here. So on the left end of it, where I have a column. Sorry, this is not my favorite app. Well, it's the best I have. It's not my favorite. Anyhow, so on the left, you see there's 0 for discontinuous or unrestrained, simply supported condition, basically. You see that, right? And for spandrel, it's 1/24, eh?
Yes.
For column is 1/16, right? So these numbers drastically different from the internal span, which is 1/11s, right?
Right.
So that influence this span only 1/10s is because of that. Okay, so that's why this is 1/10s, this is 1/11s. So when you calculate On the interior surface of the end span, which is this span only, negative is 1/10. But you design for the other one, which is also negative, but it's 1/11.
Okay.
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 You need to do both. You need to do both.
All right. Thank you.
Yeah, sure. And then think about it, and it's gonna be symmetric usually, right? For structured design, it's always symmetric, right?
Mm-hmm.
So the other side will have the same thing. If per se, if I have the same column end up here, right? Like just like that, right? So you essentially copy the same thing over here. Get it?
Okay.
So for example, if this is 1/11, only if this span is internal span. Only if
Right.
if this is end span just like that, then this is no longer 1/11. It becomes 1/10.
Right.
Right?
And so would it be okay if we just did 1/2 and then said that the other half was just identical, basically?
Yeah, that's typically what happens, right? Typically what happens. Say, for example, let me go back to this. We'll just talk about it. Right here, right? So this is the typical example, right? So if I look at the slab, I'm talking about here. Oh, oops. I'm looking at the slab right here, okay? Can you see it?
Mm-hmm.
Okay, so the symmetry is right here.
Right.
So I only need to consider this half.
Okay.
Okay. Now for the beam, I'm drawing here. I'm gonna use red here. So the symmetry line is right here. Right? So I'm gonna only consider this right here.
Okay.
Okay.
Actually, I had one more question. So for the beam design, the beam design also has the weight of the slab on top of it, right?
You need to consider that. You need to consider that, right? So that has a little bit tricky question here because think of it, right? I forgot to mention that. Thank you for bringing it up. So think of it, right? On this beam right here, this fellow here, right? This fellow here, and actually takes half of the slab in this span here and half of the slab this here. So this shaded area is how much of a slab they're taking care of.
Oh, okay, yep.
Right, so that's what it is.
All right, thank you.
No problem, no problem. Good questions, right? Very good questions. Any other questions? Any other questions? Any other questions? Okay, so I realize that's been a little bit challenging to interact with you guys on this video thing. And I hope I can talk to you more on Tuesday, tomorrow, when I have a review session. So if you have any other question related to the homeworks or related to the content itself, do show up in tomorrow's review lectures and we will talk about them together, okay? We'll talk about them together, okay? And I will upload these lecture notes to the Canvas as well. So recorded video as well, so you can see them when you have time. For the beam is a slab on top of the beam. Yes, indeed, right? So this is the beam, right? And this is another beam on the edge or on the frame, and the slab is right on top of this. Right? Slab is another. What time the review session is? Always 2 o'clock every Tuesday, right? I sent out an email before, it's always 2 o'clock every Tuesday. Okay? Yes. All right, any other questions? Any other questions? Second guess about what we did here? Any doubt? Any confusions? Okay. I want to mark 4 because I have a lot to cover, but you're welcome to ask me any questions in the email and all, and I'll send you an individual link to your homework feedback. It seems like that's the only way it's going to work now. Okay. All right. So without further ado, let's give me another 10 minutes. Open up for the next things. Okay. Now. Let's review a little bit what happens last lecture, right? So last lecture we talked about, oh shoot, sorry here. Last lecture we talked about deflection. One of the critical things is calculating moment inertia for cracked, uncracked cases, right? Cracked, uncracked cases. So these are uncracked and these are cracked, okay? I also attached, right? Sean, we just said it in the beginning of the lecture, you probably missed it. The review is tomorrow, Tuesday, 2 o'clock. All right, that's the review, okay? All right, so coming back to the serviceability deflection. So we talk about moment of inertia for uncracked and cracked cases. And I also uploaded a handout for compressive reinforcement. Okay, it's not really difficult, but just adding another layer of concrete on top of it. Okay, take a look at that, and if you have any questions, we can talk about it. But now let's open up the next question. Right? What is the next question? Is the serviceability. All right. So I'm running out of time, so I'm just gonna start this real quick. Okay. Give you a little bit flavor of what it is. Okay. Now think of this. Right? So I have a beam, simply supported condition, right? Simply supported condition. I have a distributed load on top. Okay, distributed load on top, right? And say this is omega. All right. Immediately, I have my midspan. Right? And this is deflection goes like this. The deflection goes like this. Deflection goes like this, right? And then I have my midspan deflection. This is the delta mid. Midspan deflection is 5 omega L to the power of 4 from statics or from mechanics material, right? 384 EI. 384 EI. Okay. And I have a end constrained, right? Fixed. This is usually cast in place, not simply supported anymore, right? I have a distributed load on top. Okay. And then the moment or the deflection goes like this, right? The deflection goes like this. And this midspan, in this case, is actually omega L4 divided by 384 EI. Okay, you notice that this is 5 times bigger than that. Okay, 5 times bigger than that. What does it mean? It means that, right? The end constraint have to be taken into consideration. End constraint.
Wouldn't you also have a single fixed end condition as well?
Yes, we will. But here I just want to illustrate shortly or quickly. End constraint has to be considered in deflection calculation. Okay. Okay. So yes, you're right, Sean. With different boundary conditions, we have different numbers always, right? But I just want to show you that it is much bigger if I have a different boundary conditions. Okay. So this is one thing I have to keep in mind, that I cannot. That is to say, I cannot simply take one formula to calculate deflections. Okay, I have to consider the whole span. The other thing, right? I also have a problem like this. Say if this is simply supported case, simply supported beam, right? A simpler condition, but I have a cracks along the span length. Okay, I have a crack along the span length, and the moment diagram, if I write it out, draw it, and this is moment diagram, right? And the distributed moment diagram looks like that, parabolic line, remember? Parabolic line, okay? And you remember from previous calculation, I have cracked moment right here. Cracked moment right here. Is that right? Cracked moment right here. Okay? Now, think of this, right? We talk about this cracked, uncracked cases. We talk about the cracked, uncracked cases. Okay? And you know that if and this is maybe the cutoff line, let me just draw it out. This is the cutoff line, right? So this is the cracked elastic range. This is uncracked. Okay. Now, if I have 2 different stages or different sections when they crack, when the surface load, and this is the apply moment right here. Okay. What I do, what I actually see is I have actually 2 sections. One's a little bit thicker. Remember when I transform that, and the other is a little bit thinner. So this is uncracked, and this is IG. Okay, so to see it, this is cracked, and this is the compressive zone, and this is a little bar equivalent area underneath it, remember? And this is the whole thing with the little wings on outside. Okay, so this is I crack, right? What does it mean? It means I cannot take only one moment of inertia to calculate the deflection. I cannot take only one moment inertia to calculate deflection. What I need to do is find out an equivalent moment inertia, i.e. effective. Okay, and ACI says, okay, this IE here is defined as effective moment of inertia. All right, moment of inertia, and it consider both. It consider both. It consider the boundary conditions and also the cracking stages, right? The cracking stages. So ACI has the equation for it, and this is MCR cracking moment divided by the applied moment to the power of cube multiplied by the gross moment inertia IG plus a bracket inside 1 minus a crack moment divided by the applied moment cube and ICR. Okay, so that is ECI's equation, empirical equation. You can find this from ACI 24.2.3. 24.2.3. And then the ACI also says, look, I can tell you how to calculate the crack moment. And we have this from previous lecture notes equal to the modulus rupture FR multiplied by the gross moment inertia IG divided by YT. Okay, you can calculate that. And the MA is applied moment. And we'll explain that in the case-by-case scenario. Okay, and then IG is the gross moment of inertia. I cracked. Is the cracked elastic that we showed you last time, transformed. Transform. Okay, so quickly to summarize here, right? What we need to consider when we calculate deflection is we cannot use one moment inertia. We have to use this effective moment inertia. And this effective moment inertia is calculated using this formula right here. Okay, that is an equation of both cracked moment, applied moment, and also the equation of both gross moment inertia at the intact section and the cracked moment inertia at the cracked section. Okay, all right. So that's what we're going to talk about next lecture in terms of deflection. Okay, so I just want to start it today. So give us an opening, and we'll talk about this on Wednesday. All right, on Wednesday. Okay, all right. Thank you guys. And if you don't have any other questions, we can end here and talk about more about this coming exam tomorrow, Tuesday, the review session. Okay. Again, I'm not going to talk about specific problem because I already showed you guys last time. We're going to go into some of the specific problem in practice. Okay, in practice, and review some of the critical concepts we have covered so far. Okay. All right. Okay. Before I end, is there any other questions? Is there any other questions regarding to the course? If you have any specific problems? Okay. And all the other specific details about the exam in terms of length and all that, we'll release that on Wednesday. But roughly, you know, right? 3 hours, 5 problems, and we'll go online. It's going to be a take home. We'll release the problem as a specific time, which I will announce, and then you have more time to work on it. Okay, you have more time to work on it. Now, let me say this. If you have any accommodation, you need more time, please send me email before this Wednesday, okay? So I know you have accommodation, so I send you the exam at a different time, okay, at a different time. Okay, don't forget about it, okay? Don't forget about it. I will remind you also tomorrow, okay? I will remind you also tomorrow, all right? Okay, well, if there are no more questions, I'm gonna stop here and we will resume our lectures on Wednesday, okay? Thank you very much and see you then. Bye now.